I wish I were there with you all right now. I just figured this might be an easier way to go over the final terms so you kind of know about the level of depth at which you need to know this stuff. So first, let's take a look at the normal distribution. We had spoken about it a little bit when we were looking at histograms, but here you'll notice, let's see, you get this basic symmetry. You're going to see that most of the scores are going to fall, in this big area here, in the central area right here, with some extreme scores falling, or outliers, if you will, falling to either side. You will also want to note that the mean, median, and mode here are all going to fall at the dead center, that mark of symmetry. If you have a perfect normal distribution, that's where it's going to be. Another thing you'll want to realize about the normal distribution is that there's a lot of things in nature that just distribute like a bell curve, just distribute like this rather naturally. Like, for example, infant birth weight. You could graph that on a bell curve for sure. Height, the average height of men in this country would be normally distributed. Other things will be normally distributed, like the number of shoe sales per size. If you're looking kind of at that mean, median, and mode, if you're a shoe salesman, you're going to sell more size 8 shoes than anything else because size 8 is the most common foot size. Another thing that will distribute normally, generally speaking, would be a person's IQ. While that is a controversial measure, it's probably an easy go-to in terms of explaining the bell curve, and so we will use that. But I want you to first kind of go back to this line here, this mean, median, and mode line. And I'm going to tell you this piece, and it's going to seem absurdly obvious, and this is the part that people will forget. But that line right there divides your data in half. I'm telling you right now, I'm going to be looking for percentages or percentiles a little bit later, and that will be the piece that people forget. You got to remember 50% on one side of the line, 50% on the other. It sounds simple, but you'll see. When we look at a bell curve, we also divide it into regions. So this area here would be one standard deviation away from that mean, median, and mode, which is right here, right? Same thing here. This amount here is one standard deviation away from the mean, median, and mode, right? And I will explain exactly how what we calculated in class fits into what we're looking at here. But first, let's look at the percentage of the population that would fall between a standard deviation of -1 and +1, or even -1 and 0. So the bulk of our population is here, so we would say 68% fall between a -1 and a +1. It's actually rounded. I can give you the specific numbers if you want. This would technically be 34.13%, which would make this 68.26%. But for our purposes, just a 68 is fine. We're not going to have to take it to those decimals. But 68% of our entire population will fall between -1 and +1 standard deviations from the mean. As we break down the next region and we go 2 standard deviations, again, away from that mean, median, and mode line, which is right here, right? 2 standard deviations away, in this direction, -2, you have 47.5% of the population. Over here, towards +2, 47.5%, and again, rounded, but you have 95% of the population falling between a -2 standard deviations from the mean and a +2 standard deviations from the mean. And the last big region right here you are at -3 standard deviations, +3 standard deviations, and the percentage of the population that falls within that area is roughly 99%. Although these numbers are rounded, like I said, that's 68%, 95%, and 99%, these are numbers that you're going to need to know. And what we're going to do with any particular data values that we have with something is we're going to standardize them by calculating the z-score. I will show you how to calculate z-scores. It's actually rather simple. I'm not going to ask you to look for the area under the curve. We won't really need to do that for our purposes, but I do want you to recognize this. And the benefit of calculating these z-scores, as they're labeled right here, and you'll notice that they line up precisely with standard deviations, right? A z-score of 0 means that your score is right exactly on the mean, or the median and mode, right? A z-score of +1 means that you are falling one standard deviation above the mean, median, and mode. The benefit of doing this is that having a z-score really tells you how you are doing compared to other people. So let's take, for example, you take a test, you get it back, and you get a 65% on it, right? I think a lot of you would probably be upset with a 65% on a test. But probably less upset if you found out that that 65% was the highest grade in the class. Similarly, you might be okay getting an 80% on a test, but that 80% might lose its appeal if you found out it was the lowest score in the class. Now let's say, for example, that you take some form of assessment and you get a score of 80. So I'll put a score of 80 right there. And on the same assessment, let's say that the mean, median, and mode is all 70, right? So there's your mean right there, 70. And I know that that 70 is going to fall right here. That's dark enough for you to see. Right there on that line, right, a 70. And now let's say that our standard deviation is, I'm working with a sample obviously here, right? Let's say our standard deviation is 5. Now, if I go one standard deviation above that 70, one standard deviation above the mean, I add 5, and that becomes 75, right? If I go another standard deviation above the mean, I would get 80. I'm adding another 5. I add another 5 again, add 3 standard deviations above the mean. Going in the other direction, I have still starting at that 70, standard deviation is still 5, I'm going to subtract 5. So 70 minus 5 would be 65, that would be the score there. They're subtracting another 5 and I get 60 here, and I'm down to 55 there. So when I look to see how I performed, this is my score, let's say right here. So that 80 would be at a z of +2. Now, so that's a pretty high score on whatever measure it is that I'm using here. But the next piece is really to kind of calculate, what percentage of the population I did as well or better than. So we're kind of hinting at the area of the curve, but we're not going to calculate it precisely. So to calculate the percentage of the population that I did as well or better than on this measure, right? First, I'm going to try to remember. I remember this number here, 99. That's taking me here from there to there, right? And so from here to here, I know that there would be, and again rounded, 49.5% of the population, right? Now, I'm not going to look at another 49.5% and just go with the 99 on that one, because that's going to lead to error. Remember, this mean, median, and mode cut my data in half, so I have to go the whole way here. And remember that there's 50% of my population over here, right? Which means I add these two things together, and at the end of the day, I would be able to say on this measure, when I add the 50 to the 49.5, that I did as well or better than 99.5% of the people who took this test. In that example that we just used with the score of 80 and the mean of 70, right, I was writing the mean here and I had my standard deviation of 5, right, so I'm adding 5 each time. I'm really sloppy on this thing, it looks like, right, to try to calculate it. It's not always going to land so succinctly on a line, exactly +2 or exactly -1 standard deviations from the mean. It's not, you're not going to get a perfect z like that in a real world. You'll get it sometimes, but not as frequently. So instead, particularly when it doesn't work out so nicely, you use this formula right here. So the z-score, let's see, the z-score right there, you take, to calculate the z-score, you take your score, which is x, minus x bar, which is the mean, and divide it by the standard deviation. So using the same numbers, I can say, okay, so my Z is it's a score of 80 minus the mean, which was 70, divided by the standard deviation, which was 5, right? So I get my Z equals 10 divided by 5, or my Z equals 2. As I'm looking at this, I would love to say that like my handwriting's just sloppy because I'm not used to using this program, but maybe that's just my handwriting. So sorry about that. Hope you can read it here across my Z's so you can tell. There you go, my Z's. And again, I'm going to use that to calculate the area under the curve, but this time I'm mostly just looking for percentiles. And one of those things that distributes normally that we will be looking at later in the year, and I said this is a controversial measure, is looking at measures of intelligence, so like IQ scores. The average IQ score so that mean, right, or mean, median, and mode, the average IQ score would be 100. The standard deviation on most IQ tests is 15. So thus you'll see like I add 15, right? So IQ of 100, I add 15 to 115, add another 15, I get 130, add another 15, 145. I subtract on this side 85, down to 70 to 55. And you kind of go back to that same idea here, though, of like the average person is going to have an IQ between 85 and 115. 68% of your population will fall there. So for a very simple question, I might say, okay, so if you take an IQ test and you end up with an IQ of 100, right, that would be a Z of 0 because you landed right on that mean, median, and mode. You also did as well or better than 50% of the people who took that test. So there you are, 50% would fall to one side, 50% to the other. Notice that I'm saying as well or better than a certain percentage when you're looking at this, because you're not talking about the percentage that you got right. You're talking about how you fared compared to other people. So let's say that you take an IQ test and you end up with an IQ of 85. So, okay, so I know that I'm right. My IQ, 85, I would be at a Z of -1, or 1 standard deviation below the mean. So then when the question comes, what percentage of the population did I do as well or better than, right? I'm going to start this way. So I'm going to be like, okay, well, I have 100% is contained in the bell curve, right? So there's my 100%. That really accounts for everything. But I didn't do as well or better than that 50%. So I'm going to subtract 50% right off the bat, right? So now I'm dealing with 50. And then you have to think, okay, so what percentage of the population falls in that zone? And rounded, that would be about 34%, right? So I'm going to subtract another 34%, and I am going to have done as well or better than 16% of the people who took IQ tests. Or really, as well or better than 16% of the population. Very often, I am going to end up with a score, though, that doesn't fall precisely on a Z, a -1, a +1, or what have you. It's going to fall somewhere in between. So let's say, for example, we're going to remember that formula that Z, okay, so that formula, Z equals your score minus the mean divided by the standard deviation. So if I have a score, let's say, of 135, so that's my Z equals 135 minus the mean's right here, 100, divided by, see what I'm adding? The standard deviation is 15. So I'm going to divide by 15. So Z equals 35 divided by 15. And that would give you something around Z equals about a positive 2.33. So looking at the bell curve here, obviously that's going to put me right around there. In a case like that, I am not going to ask you to calculate the percentage of people you did as well or better than, because you would need a chart to do that. And we really just need to understand this from a conceptual perspective. When it comes to practicing, part of it's going to be just plugging in z-scores and seeing where you fall. But some of it is also calculating the area under the curve, when it's not at the 68, 95, 99. So for example, if I were to take a z-score of +2 and a z-score of -3, and I wanted to calculate what percentage of the population really fall between those 2 points, I take what I know about that 68, right? So I know I've got the 68 covered between here and here. I really have horrible handwriting. Wow. I don't have time to fix this. That 95 is going to fall between here and here, right? So I know that that number is going to be over 95%. So I'm really now just looking to add whatever the area was here. So the number I'm going to come up with is going to be rounded to about 97%. So I would take some time making sure you know the areas between two z-scores, whatever they are, and then also saying okay, so if I have a test and this is the mean and this is the score, this is the standard deviation, where would this fall? Just practice with some calculations. And sort of the next little piece is when that normal distribution doesn't look so normal. You've lost your symmetry on it. And that's one thing I want you to remember from that example when we were looking at central tendency with people moving onto that street and dealing with the house at where you're all at mile markers, but you've got that one that's far away at mile marker 98 and the rest of you are at 1. I think there was 2 at 6. Was there one at 9 and 15, something like that. But what you notice is that they were all kind of between 1 and 15-ish, and then they had one way off at 98. You're dealing with outliers. And as you remember, the mean pulls towards the outliers. The median is unaffected. So in a normal distribution, that means, you get that nice symmetry, right? You're going to, wow. That's wonderful. I'm just going to leave it there. But that you get that nice symmetry, wow, even better. Where the mean, median, mode fall there, it splits the data in half, right? But if you have outliers, the mean is going to pull towards your outliers, which means that the mean, median, and mode are not going to be all in the same spot now. That mean will chase the outliers. So if you look at, in the case of, let's say, a positive skew, I have to erase that thing. This just looks absurd. Let me get rid of that. Sorry. There you go. That is ridiculous. But if you just look at, here, in the case of a positive skew, that means you're going to have an outlier up high, right? So if you come into class and I say, oh, the test scores that were positively skewed, you're not going to want to hear that, because that means that most of the data points are going to fall to the left, and you have maybe 1 or 2 people that did well on it, and they're going to be pulling the mean towards them a little bit. They're going to be pulling up the average of the class. You really don't want to hear about a positive skew. You would rather it be a negative skew. A negative skew means that maybe there's a person or two that's pulling the average down. It's going to pull the mean in that direction. But most of the scores fell on the higher end. So remember this, when you're looking at the title, a positive skew, the skew is telling you where the tail is the longest, because the mean is going to pull towards the outliers, right? So the mean is going to be over, over here, in the positive skew, it's going to be over here. It's going to pull, it's not going to be that far over, but it's going to pull towards the outliers. The median will be unaffected. The median is still going to be the shortest distance between all points. In the case of a negative skew, the mean is going to come first, going from left to right, and then the median. But again, remember, the skew is telling you where the tail is the longest. So negative skew means the tail is longest on the negative side or towards the left. Most of the data points would then fall towards the right. And a few final things here. When we're looking at statistical significance, first of all, I'm not going to make you calculate it, so you just need to recognize it is all. But when you take your English class or even a social studies class and they say, well, you're talking about something and somebody says, well, that's significant, they're usually saying that it's important. And for our purposes, when I'm saying something is significant, I'm not saying it's important. What I'm saying is right here. It means, so if I say something is statistically significant, I'm not saying it's important. It may be quite unimportant, actually. Who knows? But what I'm saying is that it's probably true, or my findings are not due to chance. So when I'm isolating my variables, I think I've located what it probably is. I've probably found it. And this is going to be called a p-value. What you want is as low of a p-value as possible. The lower the p-value, the more likely it is that the results you're looking at did not occur by chance. So I give you an example here. 95% chance of being true looks like a p-value of 0.05, meaning that there's a 5% chance of it not being true. And on a very basic level, I'll explain sort of where these numbers are coming from. But if you are, to find the significance level of something, you're going to subtract the number shown from 1. So if I take, for example, a value or a p-value of 0.01, right, so let's see, I'll write that there so we don't forget. So let's say the number I'm working with is 0.01. Okay, so that means that there is a 99% chance of it being true. What I'm going to do is subtract that number, that 0.01, from 1. So 1 minus 0.01 is going to give me 0.99. I'm going to times it by 100. And I'm going to get a 99% chance of it being true. And as I went through that whole thing, I'm realizing that I may have complicated it for you, and I don't mean to, because I'm actually not going to have you run any type of statistical test. Here's what I want you to know. If you see a p-value, you want the p-value to be ideally as low as possible, right? So it's going to be a number under 1. And like you're looking at okay, so if we're looking at 0.05, that's a pretty good p-value, right? 0.05 is good, 0.01 is even better, 0.001 better still, because then it's a 99.9% chance that it's probably true. So that's what we're looking for statistical significance. We're looking really, we want that low number. 0.05, lower, would be even better. If you see it as a percent, then you're just saying okay, so I want a 95% chance or really better of it being true, of what I'm looking at being true. And when you're looking at research, and I think we started this whole unit this way of, with that example with the cards, with the triangles on one side and the circles on the other, you're not looking to prove something, or you're not looking to only prove something, I should say. You are looking to also see if you can disprove something. And so one of the things, we're not going to calculate this either, but one of the things that you would do in research is set up your hypothesis and your null hypothesis. And ultimately, right, the hypothesis is what you think is true. The null hypothesis is really the reverse of what you think is true. I'm going to explain that. But you have to look to contradict yourself. You can't just look to see that you are right. You also have to consider that maybe you are wrong. So let's say an experimenter was hypothesizing that alcohol has a negative effect on your motor tasks. So essentially, I'm saying, okay, so you drink more alcohol, your ability to do motor tasks, whether it's writing, playing the piano, or gross motor tasks like walking and running or stuff, it's going to be impaired, right? So the null hypothesis isn't going to be, alcohol helps these things. Nope, it's not going to be that. It's going to be alcohol has no effect. So so alcohol has a harmful effect, would be my hypothesis. Alcohol has no effect would be the null hypothesis. And if the experimental data shows sufficiently that alcohol has a large negative effect on one's ability to do motor tasks, then the null hypothesis that alcohol has no effect on these motor tasks can be rejected. One slide left. We are so almost there. Here we go. Ethics. So when conducting any type of research experiment, you have ethical guidelines that you have to follow. Obviously you want to get something past an IRB, get approval to run any type of survey, experiment, what have you. But it's never going to get past an IRB if you are breaking ethical procedures. So these are a few big ones that you will have to keep in mind. The first is informed consent. Informed consent, really, you have to tell people, here's the nature of the study. If there are physical risks, lay them out. What are they? Are you going to be uncomfortable? Are you going to have unpleasant emotional experiences? Whatever it is, you have to tell them to the extent that it doesn't have any impact on the experiment that you're doing. In informed consent, you also have to let the subjects know that they can withdraw from your experiment at any time. So signing up to do it, saying yes to it, doesn't mean that they have to stick with it. Next up would be restricted or careful use of deception. If it is necessary in your study to deceive the participants, you have to do that very carefully. There has to be good reasons for it. You can't have any harmful effects to that. And then afterwards, you are going to have to debrief. You're going to have to tell them, like if you were looking to change their attitude on something, you have to kind of explain the process and what you lied about and why you lied about it, all the reasons for the deception, and you have to clear up really any misconceptions. Confidentiality is also extremely important when considering the ethics of research studies. So all information that is provided to you is private. And when you report on information, you can't give out any identifying markers. Like you can't say anything that would ultimately lead people to know who it was you were talking about in your study. You can't do it. And now there's the choice given to students as to participation. You're going to find this a bit in college where you'll have a professor working on some type of research and they try to get their students involved in it. Maybe as part of a grade, but if it's their research, you actually are given a choice. You have to be given a choice to participate in the study or not. When it's part of a class, you kind of get stuck doing something though. So it's like, all right, so I'm doing this research study. I want you to be part of it. If you decide that you don't want to be part of it, you're allowed to make that choice. So you're probably going to be writing like an additional research paper or something. They're going to make you do another assignment to make up for it, but they cannot force you to participate in research if you do not want to. And lastly, probably the most important is you can't do anything that may harm someone. You will see when we're looking at some of the psychological studies that have been done, some of these rules were definitely broken. But we'll go through those in other units.